Hi everyone, we're Group 7 and today we're going to talk about the XLab project that we completed this semester. My name's Jaden.
And my name is Joseph.
My name is Eric.
I'm Sydney.
And my name is Eli.
We're all third-year students pursuing degrees in mechanical engineering. This semester, for our 300 level design class, we developed a fatigue testing apparatus based on the R.R. Moore rotating beam fatigue system.
The setup primarily consists of a motor that spins the shaft, 4 bearings, and 2 encoders. The 2 outer bearings support the shaft, and the 2 inner bearings apply a load through a string pulley setup that connects to a load cell. Putting the string on this 4-point bending setup instills a constant moment along the thin middle section of the shaft. This results in maximum stresses on the outer fibers of the test specimen at its thinnest cross-sectional area, with maximum compressive stresses on top and maximum tensile stresses on the bottom. The rotation of the shaft causes the locations of these min and max stresses to constantly oscillate. At high RPMs, a shaft can have cyclic stresses applied to quickly determine the fatigue characteristics of different infills.
As you can see here, both the size and the fidelity of the R.R. Moore experimental setup are greatly reduced. The class believes that this form of the experiment will sufficiently quantify the fatigue properties of the 3D printed plastic shafts. Our team's setup is slightly modified from the proposed design. We chose to use a load cell to measure the load output on the setup over time to test the hypothesis that FDM 3D printed PLA strain weakens over time. If the load decreases over time, the team believes that this means that the distance that the string travels shortens, reducing the length the string has to travel from end to end, and therefore decreasing the deflection that the load cell measures. We have also made some augmentations to the electronic setup. We have added a transistor to step voltage down from 12 volts to 5 volts. This allows us to have one plug into the wall that manages all our power. Additionally, a relay has been added to trip the motor when a shaft breaks, allowing the team to easily identify failure. Failure is detected by the encoders and optocouplers when a difference in RPMs is measured at the 2 ends of the shaft. The optocouplers work best with encoders of darker colors, so when we printed red or white encoders, we colored them over with a Sharpie.
We also decided to measure the effects of infill geometry on the specimen. All the specimens tested were printed with similar settings, but because of limited access to printers and limited time, we couldn't print all the shafts in the same batch or with the same color filament or even on the same printer. However, we solely used one brand and chemical composition of filament and printed the samples on the same model on Age printers. We used Ender 3 printers and the print settings can be seen here.
We were able to run a total of 5 trials, 3 of which resulted in broken specimens, and 1 that we believe ran under the fatigue limit for almost 3 days. One of the failures occurred at the system level, a fractured motor coupler, but the 2 other ones occurred at the specimen. From the 3 trials that we successfully collected data from, we were able to form a list of the most likely errors affecting the observed data.
The more likely causes for the trends in the data present themselves in our low fidelity experimental setup. There are 5 different ways that we believe the trends could show themselves. First, the team thinks that the gradual downward trend in the load cell readings may be due to string creep over time. In addition to string creep, there's also observed creep in the 3D printed functional components like the bearings and the mounts that were made from PLA. This would have to be addressed using higher fidelity metal parts. Perhaps parts could be redesigned to be water jetted out of aluminum or steel.
The bearings also undergo great amounts of friction. When running, the entire setup experiences vibration. In order to avoid error from this, we place the setup onto foam blocks to absorb the energy. However, this vibration can still be seen causing friction on the bearings, which in turn increases the vibration. Another possible reason for the trends observed in the data is our low fidelity data collection system. We suspect that the trends seen in the data, such as noise and sudden jump in load, might be from the variation in the voltage supply over time. This may be because the circuit was powered directly from the wall power and no voltage regulator to maintain the voltage supply. We also suspect that the load reading may be drifting over time because of its low quality.
As you can see here, we believe that there was possible fatigue softening, hardening, and then more softening. This is a complex result that necessitates a more robust, error-proof experiment setup to prove. Further research must be done to determine if such behavior is really occurring or if it's simply a result of our experimental error.
Throughout the multiple fatigue test runs, we were able to gain all this valuable information about the effect of an applied moment onto a rotating shaft and the best ways to measure the failure of this system.